Hello there. Welcome back. Good afternoon, everyone. So I see that the survey, pre-survey link has been posted. I would appreciate if you can take a few minutes to do that, and then we can start the presentation. Hello there. If we are done with the survey, we can get going. Can everyone see the slide on my computer that I have shared?
Yes.
Okay, so are we done with the survey? Okay, so as the title indicates, this is a very introductory tutorial to digital data uh, and the provenance and current thinking says, where we started and where we are today. I felt it's important, especially you being non-computer students, non-computer science students, it would be useful to know the evolution, what we have been doing and where we are. I would think that you are really the blessed ones with the technology and the power of the computers that we have. And this was really not so some time ago. So that's me. So I'm not making any assumptions in this tutorial. Uh, this is meant for undergraduate computer science high school students and non-computer science students. So the focus will be on the data collection, storage, cleaning, loading, management, analysis, and how we have been addressing that with computers. And even before that, since you'll be doing a lot of different kinds of analysis in your domain and maybe in other domain, I think it's important to understand this. So the outline is motivation, a brief understanding of the terminology, what is data, information, knowledge, and wisdom, and early enablers for creating data. How did we go from analog to digital, and what sort of precipitated the need for automation? And the important thing I think you will see again and again is the changing requirements. We have some things available today. It is not enough. We need better things, more things, and that prompts a cycle of changes, changes to improve different aspects. And that has been what is happening over the last 50, 60 years. So we will trace sort of the provenance or progress from flat files to what we call data science and analysis today. And if time permits, I will go over some real world data analysis examples and then conclude. So if you have a question, please raise your hand with Teams so that I can see you clearly. And then you can turn it off after that, or you can put in the chat. There is a moderator who can help me towards the end to answer your questions. I want to make sure that what everything is understood clearly, even if I have to go slow and not cover everything. So it's not how much I want to cover, but to make sure that you understand what we cover. So motivation is, you're given a data set, some description of the data set, and you know the application area. Your boss or advisor wants you to figure out how to leverage this data set for improving the business or understanding what's going on. So this is the fundamental problem that is driving data mining, data analysis, everything we do. And this is an example from the business domain, but it could be for research, generating more customers, retaining current customers, prevent them. This is very common in the mobile phone industry, as you may be familiar with. How does this business compare with others? So if you go to vaccine, we had COVID, is there a booster shot needed? Of course, the company that markets it wants it because that is their business, but we do some independent analysis by CDC, FDC to determine whether that is actually necessary or not. So there are different players trying to do different things, and how do we understand all that? How do you decide? Is it possible to analyze? It is possible to analyze this data in so many different ways. Which one is better? Which one will you choose? And the justification for it. Most importantly, I think this is many times missed by our students. How will you validate your results? This is very important because what I tell my students, and I want everyone to understand, is when you run a program, you will get a result. That doesn't mean the result is correct. There is this assumption that just because you got an output, it has to be correct. That is really not true in many cases. So this is something that you have to constantly worry about. At the end of the day, you need to convince your boss that and your solution is good and it works with high probability, and then you go from there. So this is in a nutshell, what is driving data analysis today and earlier. So I call it analysts without borders, just like doctors without borders. And the reason for that is that you can no longer just do analysis in your own domain. You need an understanding of multiple topics, multiple domains, and be able to synthesize your analysis and results in many ways. So you cannot just focus on a programming language or an operating system or a particular type of data. And data analysis itself has many steps, meaning choosing meaningful attributes for data for analysis, mining, machine learning, algorithm, probability and statistic, drill down visualization. So you have to be careful in what you choose, how you choose, why you choose. So my advice to a lot of students who do this is do not become a person with a hammer looking for a nail. If you have a hammer, everything looks like a nail. Instead, become a person who can match the tool for the specific problem. This is the most difficult part of it. So this is where you have to consciously make sure that you are doing the right thing and not just applying what you know, but what is actually needed. So this is just to understand, Sherlock Holmes say it is a capital mistake to theorize before one has data. Interestingly, one begins to twist the facts to suit theories instead of theories to explain the facts. This is very true. I've seen students come to me and present their experimental results, and they say, yeah, everything is fine, correct. When you start digging deeper and asking questions, then you realize this may or may not be right. I think that is the process that humans have to do. You, as students, have to constantly question and make sure everything is correct. Many programming mistakes are discovered after the results are explained or sometimes even published. That's why we need to worry about independent validation mechanisms. So hence, two or more independent approaches should always be used for validation. We try to use, theoretical and analytical way of figuring out what to expect and see whether they can be matched experimentally. Just using only one of them may not lead to the correct thing. Also, do sanity checks on your outcomes to make sure you have not overlooked anything. Always make sure your test cases include boundary cases. So there's a tendency for the person who is doing the programming to test only cases that work because they know what they have done. And this is going to be a costly mistake. That's why most of the companies, if you look at Microsoft, they have as many testers as many developers. Testers should be different from developers so that they are not subject to knowing what has been implemented and testing only those features. So some clarifications, why learn programming for analysis? Today, you have a lot of packages for many tasks you need to do. You may have to use appropriate data structures and populate. So it is not that you're developing a lot of code, but you need to sort of put together the packages in a way that is appropriate for your analysis. Choosing appropriate algorithms for what you want to do, figuring out plotting and visualization, generating good and understandable reports. Does the data set used for learning matter? It's a difficult question, and the answer is yes and no. It is important to understand that analysis, no matter what data set you use, is the same. You're doing the analysis and you should be interested in understanding the process of analysis and what you are trying to do based upon the context and the data set and the application. So you'll be encountering different and complex data sets all the time. Do not get hung up on the latest applications. There is a tendency, at least among computer science students, to say, okay, I only want to use Python. I don't want to be using anything else. I think that is not the best way. It is not the language. It's what you want to do with the language. Some languages may have a easier learning curve. Some may be a little more than that. But languages change. Today it's Python, tomorrow it's something else. Process of analysis does not change. Some pre-processing and other details may change. So if you have any questions, please. So I see one hand up here. Go from the few days. Jessica, your hand is up. So how will you cover all we are going to encounter in our career from this workshop or from this analysis method? The simple answer is we cannot. But the more important thing is we do not have it. As I said, the process remains the same. Details of analysis depends upon the business domain objectives. So please focus on learning the analysis process, not just on the data sets. At some point, you need to understand the data set. Please focus on presentation, visualization, and how you can correctly analyze and benefit from that. What about different types of pre-processing? Same as above, may have to add more tools to your pre-processing toolbox. At the end of the day, domain knowledge coupled with analysis process is what is important to be a successful data analyst. When I say data analyst, it can be from any domain. It shouldn't really matter at all. The reason that you need domain knowledge is that you have to be able to understand the data and what you're expecting, or if you get something through the analysis which is counterintuitive, are you be able to evaluate it? Now we have started a new program, data science program in our department, and it has been going on for 2 years now. And I was involved in the development of the course. And for this program, we specifically admit students from different disciplines. I have had students from at least 10 different disciplines in this course. And the basic idea is that we need different people from different domains to do the data analysis correctly. And that has been very, very difficult because most of the people who try to do the analysis are computer science people. They don't know biology, they don't know earth science, they don't know water management, and that makes it extremely difficult to do the analysis properly. So this data analysis, how much we want to think that, this is new, it is not. Back in 1982, without revealing my age, we are drowning in information but starved for knowledge. This was a statement made by Naismith. This was 40 years ago. This level of information is clearly impossible to be handled by present means. Uncontrolled and unorganized information is no longer a resource in an information society. Instead, it becomes an impediment. This statement, I believe, is still true today, and it will be true for the foreseeable future. So it is not enough to store, organize, and manage information, but it is critical to extract relevant knowledge and make it available for decision making anytime. This is the key. I mean, just collecting data is not very useful. You may have all the data, but you cannot make decisions, actionable decisions in a timely manner. If there is a flood, you need to know where the help need to be given, which places in that, by looking at what is going on today rather than just sitting on data. So what is data, information, and knowledge? So this is an old diagram again, which sort of classifies it into a hierarchy, which is a pretty good organization, in my opinion. So you have data at the lowest level that you collect. We also call it raw data. Then you have information where you have some additional information on data. We will see later that metadata can be a way of converting data into an understandable information. Then there is knowledge. That's what we want to derive out of this. And finally, wisdom. I think we still don't know how to automate deriving wisdom. Humans do it, and we still don't understand how exactly we do that. So here is another way to look at it, to say, data, understanding of data versus how they may be connected or related to each other. So you have data and you have information, which is a small difference, understanding what it is. But the more important thing is you're trying to understand the patterns in the data. That's what we call knowledge discovery or mining or inference, whatever you call it. And finally, one would be able to understand principles out of it, which is a lot more difficult than one thinks. So we still never say that you are doing wisdom discovery. We are only doing knowledge discovery at this point in our saga. So the basic idea is to go from data to information to knowledge to decision and to action, irrespective of the field. Casting this problem as a data processing problem, so this is my view of looking at this problem. So we have raw data, different kinds of raw data. We'll see another diagram that explains it better. And you are interested in knowledge, if not wisdom, at least timely, actionable knowledge. It may be in the form of rules, actions, inferences, predictions, and you want to make decisions out of it. So the reason it has been shown as an inverted triangle is that you are reducing vast amounts of raw data into consumable data. That is the key for what we do as part of data analytics. And it involves various things listed here: understanding relations, understanding patterns, and if possible, derive principles. So this is the process we have been doing with or without computers, right? Even without computers, the process is the same. With computers, you can deal with large data, different types of data, do it faster, do it in multiple ways. So that is the basic difference between what we were doing earlier, and this is only going to get better. So here is a data or raw data, as we call it. In your domain, you can think of just having two numbers, lat long. If you don't know that they are lat long, it has no meaning, even though there are two numbers. But knowing that it is lat long gives you a better understanding of where it can be used and how it can be used. So suppose I give you these pieces of raw data, 480,000, Einstein male 3.14. This is raw data. This doesn't mean anything by itself, but if I add some information, a data by itself is difficult to understand, and we are collecting a lot of them. I think this can be easily related to the need for fair principles and also metadata. So information in some way can be thought of adding additional context to data, which can be metadata for understanding. For example, if I say 480,000 deaths in US is from cigarette smoking, that puts a context to this number. If I say 3.14 is the value of pi, that makes it understandable. Einstein, a scientist, and so on. So you can see that numbers by themselves, whether they are numbers or strings or other things, will not be very helpful without additional information. We will come to this on Wednesday, I think, when we discuss more about metadata. So data science is the science of going from one form to another form. It can be a bunch of techniques, it can be approaches, tools, abstractions. We'll see all of this. We'll see some notions of abstractions in databases, for example, different tools in mining, and different ways of doing things. So not at all new. What is new is the size with which we can deal with, the variety of data. Earlier, we were only doing with numbers. Now we can deal with images and video and EKG and MRI. So there are so many different types of data, and the complexity, they keep changing. They actually keep increasing. Visualization is possible today, which was not possible. So the whole idea is how to cope with these things, even though the basic process more or less remains the same. Any questions? So just to give you, what is information? Briefly, or well, you can divide it into analog and digital. So digital came around not very long ago. Analog has been around for a longer time. And digital, kind of one way to think of it is pre-database management systems, post-database management systems, and post-internet. If anybody is interested in understanding a lot about information and how it was done, there's a very nice book by this author, James Gleick. It's a very interesting, but it's a very huge book, 1,000+ pages. So Shannon was the first one to introduce the word bit in 1948 as a unit of measurement of information. So bit is taken for granted today. You have 32 bits in a computer, in what we use, 64-bit computers. There was no way to measure information before. Introduce the notion of redundancy. We will come to that in databases. Redundancy can have good things and bad things to correct errors in transformation. Interestingly, the notion of error correction was used by drummers in, if you read that book, you will see in Africa by using extra words for disambiguation, they were communicating from one village to another for hundreds of years before the digital revolution. So here are a couple of questions. There were some transformative events in the history of human saga that really created the need for dealing with large amounts of data. So information were produced manually, thereby limiting the amount of information produced. So there was a time when books were produced by copying them manually and then making them available. Two transformative events in the last 1,000 years changed that significantly. Can you guess what those two events are? Anyone? You know it?
Maybe one of them is the Industrial Revolution.
Okay. That, yeah, okay. I can relate to that. Anybody else? The Industrial Revolution certainly changed a lot of things. So here is the first one. Printing press. It was in 1454. Just to understand the impact of that technology, this is way before computers, right? Look at the number of copies of manuscripts that went up from 0 to, this is 1 trillion. So this revolutionized the availability of data in some form. And that was first thing that really changed everything, because people did not have to copy books and manuscripts anymore. They could easily print it and make it available. That was the first revolution. And the next revolution came almost several hundred years later. Can anybody guess what it is? Okay, here it is. Internet. Internet again changed the availability of information from very small amount into zettabytes. 1 zettabyte is a 1 tera gigabyte. It has lots of zeros in front of it. So you can imagine, and this is doubling or going up every year. So this is what is happening to data as we speak. The amount of data is growing. So other enablers, inexpensive sensors and devices, mobile devices capable of recording image and video. Today, I'm not sure how much video is taken and whether anybody even bothers to look at it. Advances in storage, we'll come back to this later. If you create all this information, there's a need to store them. And storage technology, as we'll see, was very primitive, not very long ago. However, analysis, fusion, and filtering data has lagged behind. So producing data is easy, relatively easy, but what to do with that and how to put it into good use or just use is a different story. And this is what we are constantly struggling with. Today, every company thinks that the data they have is proprietary, make it proprietary because they're sitting on a gold mine, but they don't know how to extract gold from that. So these events that came about due to technological advances also meant that it is just not enough to create volumes of data. What do we do this with this information or data? So I'm just listing some things. So satellite images, you guys deal with satellite images, maps, and cartography. Physicists deal with Hadron Collider, which is in Bern, Switzerland, that generates tons of data. USGS, you're familiar with. I don't have to say anything. How can it be used for different purposes? Now the burden of storing, processing, and analysis is even greater, which meant that in addition to technological advances, we need to develop algorithms, mining, and other techniques to make use of them. So this is what we are trying to understand. And I think the FAIR principle is critical in your area. On Wednesday, I'll say a little bit about how we are managing in computer science without any principle that I know of. This is one of the challenges for data science. So most of you may or may not have seen a mainframe, let alone what a computer looked like before the mainframe. We are mainly know, laptops and tablets and mobile phones, which are as powerful as some of the high performance computers. A lot of people today grow up with a very powerful computer in their pocket. For them, it's very difficult to imagine a world where one had to go to a computer center to submit a job, wait for 1 or 2 days to get the results. This is how it was when I was a student, both undergraduate and graduate, where we had to go to a place where we submit our program in a deck of cards and then go back the next day to pick up an output. Just imagine one syntax error meant you lost 1 day. So this is how things were being done. Indeed, we have come a long way. Let's understand a little bit of the lineage. So this is how a computer looked like in the 60s and 70s. This is a computer from Russia. I worked on one of these computers in this series. So what would be interesting for you to know is that the memory it had was 32K words. Today we have 256 GB in our pockets. Could program through console using machine language. This was the console. It had paper tapes and card inputs. It had a very rugged magnetic tapes, no disks at all, and poor memory. So it occupied an entire room, and its capability was very, very minuscule compared to what you have today. So this is another early version. This uses printed circuits, whereas this one did not even use printed circuits. Here is a IBM 360, one of the very famous mainframes from IBM. This came about in the 70s, and it was big, but much more sophisticated than what I showed you before. And it had a large memory, which was 512K bytes. And it had disks. So here is a picture of a disk, which is almost like the size of a fridge, and it only held 5 megabytes. So here is another view of an IBM mainframe with tape drives. Tape drives were very popular, and I don't think any of you might have seen that. And this could hold a lot of data compared to the disks at that time. So they were very widely used, and they have some limitations. And here is another example of a disk drive. And this one held 50 megabytes. This was like a dishwasher. So this is where we have come in the last 50, 60 years. This was another one on which I worked on, which is the Russian replica of IBM 360. Very interesting story. Now, we have computers in all shapes and sizes, from sensors to server farms. A few years ago, I was in Sweden, northern part of Sweden, and somebody told me that there is a Facebook server farm in the north of Sweden. So kind of we took a drive to go and see. It was of course, area that you could not enter, but it was like 1 kilometer by 1 kilometer, and a building in which, I don't know, 10,000, 100,000 servers were housed. So why did they choose? Can anyone guess why they chose Sweden and northern part of Sweden to house their server farm? This is very common, by the way. Anybody? Well, these machines generate a lot of heat. Cooling these machines is very expensive. And in the northern part of Sweden, it's cold most of the time. So they don't have to spend a lot of money on air conditioning. So that is why a lot of these server farms are located in Norway, Sweden, Finland, and other places where cooling is available in plenty and without much cost. Today, you can even program your dimmer switch. Reports of flexible, rollable screens, Google Plus, embedded system. So I don't know how many have any of you heard of ChatGPT? Anybody? If you have not, you should look it up. This is the latest phrase in AI. This is something that has been put out by, this is all over the news today. And we are concerned, the College of Engineering is sending a questionnaire to understand how many faculty from other departments know about it and what we can do about it from an instruction perspective. Okay, coming to data and its management. So so we have come to the point where we have a machine which has file-based data management, mostly sitting on a disk. And if you want to use file-based systems, we can see later, the complete burden of how to use this data is on the user, means application developer. You have to understand the format of the file, you have to understand the record format, you have to know each field, you have to write your program, and if you want to change anything, you have to change your program. So this is where we started off with. Then came what we call database management systems. And it provided a bunch of improvements. Again, we'll see a little bit in this module and a little bit later. Provide standards, integrity, querying capability, interoperability, etc. Again, this sort of fell short in many other ways. So data warehouses were developed, which did multidimensional analysis and other kinds of things that could not be done by a traditional DBMS. Then there was data mining, early approaches, large data scalability, machine learning algorithms. Then there was stream data processing for dealing with different kinds of data that were coming. Today, it was developed for sensor data, but today the data coming from Twitter, for example, can be seen as a stream data because you're generating very large volumes of data in a very short time. And the rate at which it comes depends upon how popular the particular topic is, etc. And finally, we have the notion of a big data, which is characterized by what we call 4 V's: volume, velocity, variety, and variance. So the vocabulary changes every few years. And this is true in computer science. I don't know about other areas. We have new terminology, new things to. So from flat file systems, we went to DBMS, to data warehousing, data mining, data stream management systems, NoSQL databases, cloud computing, big data analytics, data science, big data analysis, neural networks. So these are the kind of the evolutionary path that has happened. From a point of view of data analysis, what does it mean? It means that what changes in requirements and advances in technology make this happen. So these things cannot happen without some underlying changes in different types of technology. It could be in hardware, it could be in software, it could be in networking, it could be in the development of new algorithms, sophisticated way of looking at things. So this goes hand in hand with each other, and we will see how this has happened. Or sometimes you wonder whether it's just old wine in a new bottle. So what is a file system? So I'm trying to understand. So when does this, just to keep track of it, when does this module end? We started at 12:45 to 1:30.
So Dr. Sharma, this will end at 2:15 and we'll have 15 minutes break, 2:30.
What time do we stop this for break?
2:15.
2:15. Okay. So basic abstraction for storing information digitally. That is a file. Very simple, yet very powerful. And believe it or not, this has not changed since its introduction. All types of information, doesn't matter what kind of information it is, has to be stored digitally as a file. Whether it's text, audio, image, maps, layers, now AI created objects, whatever it is. User decides how to store information in a file, typically as records, fields, and values within a record for structured data. Application has to understand that to interpret it correctly. The application types can be broadly classified into 3 categories. Computation intensive applications. There are a lot of different computations or applications that rely on heavy computation, finite element analysis, computer design, simulations, numerical analysis. The sort of the hallmark of this kind of computation is you load all data into memory and then process. Some of the simulations and other things that are done can take hours and sometimes days. Then we have the data intensive applications, which have lots and lots of data, and you have to deal with that data. So today, almost, if you think of Amazon, airline reservations, data of Homeland Security, USGS, they're all data intensive applications. And the hallmark of this is you cannot load the whole thing into the memory because we don't have enough memory, and then do the computation. You have to stage data from disk to memory and process it. This is the difficult part. So you have to determine how to stage data, how to process it. And that is where database management systems came into picture. And then, of course, we have the combination where we have computation and data intensive applications where you need both. You have large amounts of data, you need heavy computation, and sort of you can think of big data applications, some of the data mining, which may use giga and terabytes of data, drill down, exploration of data warehouse, dimensional analysis, and so on and so forth. So kind of all three are there. One has to deal with that and then figure out which one you are dealing with and how to deal with. So applications need to be aware of data. So just looking at file system, I mean, you will see an example, sorry, or you might already be familiar with what we call CSV files that are used for data analysis. These were not there earlier. It was being done differently, makes it difficult to change the format once design enhancement is differently. So this is the biggest problem. Once you decide on the format, all the applications. So think of it, if 50 applications are running over this file, and if you change the format, you have to revise all the 50 applications. This is the biggest problem we have in the software industry. We don't want this one change affecting so much. If the format is changed, all applications have to change. Application management is difficult, labor intensive, and prone to errors. So there is a very strong coupling or dependency between application and the storage form, which makes developers' life difficult. So we will discuss this again in the integration module, what are the different ways to work on this one. So dealing with data, multiple ways to overcome standards for representation of data and exchange of data. Use of metadata, we'll also see that later. Use of database management systems, we'll see that on Wednesday. And there has been a number of data exchange formats to exchange data, such as XML that you might be familiar with, or JSON, for which programming language support is available. Related issues are interoperability, how to make multiple applications work together without having to change them again and again every time something changes. So DBMS was one of the approaches or alternatives that came about to overcome this problem. Specifically, the problems associated with file representation and file formats. And how was it done? It was done by decoupling the data representation from application software. So if you separate them, and application software does not have to understand the data representation, then you can change data representation without affecting the applications. And this is not trivial to do. This is a very common practice in computer science. We call it a level of indirection. You may also think of it as a middleware, a very specific middleware. We will discuss this further in another module. This requires software which can bridge this gap. So software is the one that sort of bridges the gap between the format representation and what the application understands. This is done providing a higher level of abstraction. This is very important. We'll see different types of abstraction for the user, and this abstraction is mapped into files or storage by a software, and sort of you can think of it as a compiler. So what do compilers do? They take your higher level programming language and convert it into machine executable language. So there is a conversion. You don't write it in machine readable language because it's very cumbersome. It's very difficult to do. But the compiler helps you. You know, if you write in Python, there is a compiler for Python. If you write in Java, there is a compiler for Java. So DBMSs specifically had mathematical underpinnings based on set theory, and this is how the RDMSs were born. We'll go into the details, but before that, we had other types of DBMSs, which are not very widely used today, but some old utility companies still use it. Network and hierarchical DBMSs, and later we have what we call NoSQL and many other systems. Any questions? Okay, so we were talking about levels of abstraction. So this is how typically it is done. Even though this diagram is for a DBMS, we have at least two levels of abstraction. One is the physical abstraction and the conceptual abstraction. And then there is a third level of abstraction, which is what the user sees or uses. And the reason for all of this is these abstractions hide what is underneath and provide a kind of a common interface. So these are known as conceptual or logical abstraction or schema, physical abstraction. So views describe how users see the data, and they don't see the actual format in which it is stored. So by changing the format, you don't affect the user view. That is the most critical part. Conceptual schema defines logical structure. Physical schema describes the files and indexes. So by adding these layers of abstractions, you are making things easy for the end user. So the whole point of this is to make the user not worry about the details of storage and implementation, but worry about the problem at hand. So this is a very common thing. So you can also think of data exchange formats that we'll see as one form of schema that can be used for in a slightly different context. So what is a DBMS? Briefly, it's a very large integrated, that's important, collection of data. Just to give you an understanding, for those of you at UTA, you guys use MyMail all the time for registration. There is a DBMS underneath. You don't see it. You use a web GUI for that, but what we have underneath is an Oracle DBMS. Whatever system you use for registration and payment of fees, likely will have it. And the DBMS typically model a real-world enterprise, in our case, university registration, and it has entities and relationships. We'll come to that. The important thing to understand is a DBMS is a software. It's a software package designed to store and manage large amounts of data. So that is the beauty of it. This integrated means that you can access multiple pieces of data from one collection. That is also true in a system like GIS or ArcGIS that people use. Why use a DBMS? It provides a bunch of advantages, data independence, as I described, and it also provides efficient access. We will not go into that. Because of the data independence, reduced application time. It maintains data integrity and security, uniform data administration, multiple users, and very importantly, recovery from crashes. So application development time is reduced, information processing was raised to a new level of abstraction. So this was a big step in the 70s. DBMSs were developed in the 70s and became very popular. Today, relational DBMSs are used almost by every enterprise and by every company, that even though it has a web front end, behind the web front end, there is a DBMS or one or more DBMSs. So just to give you a brief understanding of how this happened. So I just want to know, without going into details, what I want you to understand here is so whatever is below this line is what has been automated or implemented by software. What is above this line is what the developer does. So I want you to pay attention to how what the developer does or the application does is shrinking. This is the whole point of almost everything we do in computer science, is to reduce the burden on the application developer or user and push more of that burden to the server, as we call it, or to the system underneath, so that that can do the heavy lifting and you only focus on the application. You don't have to worry about modeling, you don't have to worry about semantics, you don't have to worry about transaction management, you don't have to worry about pre-processing. So this is what is done all the time. This is the evolution that is taking place. And the same thing, you can see that mining has also been to some extent pushed into that, XML support and various other things. So this is what makes it, even in GIS, I'm sure when you deal with a system like GIS, you are more focusing more on the application, not on the file data formats or whether it has multiple data models, for example, and how it is used. So that is the key for data analysis, data usage, and so this is an architecture I'll skip. Usually DBMSs are very large. They have hundreds of thousands of codes. Actually, Oracle is like 1 million plus lines of C++ code. So it's a huge beast. Um, Developing, managing, and maintaining is a complex task. So DBMSs have worked well for over actually more than 3 decades. It still does. Nowadays, it does behind the scenes, like MyMap, used for payroll, airline reservation, inventory management, financial data, and more. Also used by Amazon, eBay, you name it. They serve well for efficient storage. Our expectations keep changing as the technology advances. We'll discuss more details of DBMS during years later. So how do databases work behind the scenes? Here is an example. So when you go to a website and when you click a few boxes and some output shows up, what is happening behind the scenes is a DBMS is being used for the data storage. These things that you put here are converted into an SQL query, and the query is run on the DBMS. The output is packaged and shown on your website. So this is the typical way today DBMSs are used. Earlier, they were used directly by sitting on the server and writing your SQL. Even that is done even today in a few places, but a lot of usage behind the DBMSs comes from how to use it behind the scenes, because there is no alternative representation to store all your data in a meaningful way, in a way that provides a bunch of characteristics that you need. So functionality provided by traditional DBMSs were no longer adequate. So this worked well for a decade or so. Then it excelled in querying. Even today, there is no search in a database. You only have to query a database. And people wanted exploration, not necessarily search, exploration of data in different ways. So data analysis need to be done in an interactive manner. functionality provided by AI and related was no longer adequate. So these are the sort of the things that prompted what we are going to see next. Business intelligence was needed on very large real-life data sets. Interactive usage was not there earlier. Everything was done sitting on a command prompt or running batch programs. Non-technical users want an easy to use system. So this is always the case. You cannot assume everyone is proficient in computer usage because your discipline is different, your domain is different. What you want to do is different. So this slide essentially tries to give you an understanding between the difference between search and query. There is a difference. So when you interact with a DBMS, you ask a query that is written in a specified language, SQL. You might have heard of it, you might have used it. Even when you search my map, they are translated behind the scenes into a SQL query. And queries give you exact matches, as we call it. In other words, they cannot give you approximate matches or similarity matches. Either it matches, your query matches something in the database, and if nothing matches, doesn't give you anything. This is perhaps one of the basic differences between search and querying. Search was around even before Google made it indispensable. Text search was very popular. Search gives what we call approximate or similar matches. In the sense that if you ask for something and if it does not find it, it will give you something similar or closer based upon how similarity or approximation is defined. And certainly Google does a very good job. Even if you type a bunch of words, it will try to match and give you some meaningful results. The important thing I want you to understand is these are known as the pull technology, because we'll see something that is not pull technology later. What do we mean by this? It means that you have to initiate something. You have to write a query and submit. You have to type a bunch of words and put it into the Google bot. Then only you get the result. So this is what we call pull technology. In contrast, there is a technology called push technology, which is very useful. So what are the drivers or enablers for going forward? So business information systems became as important to corporations as transaction systems. So they could not do kind of business analysis using traditional DBMSs, or it was difficult to do. They could not store multiple years of data online because of the storage limitations and the performance limitations. Mass personalization and leveraging data was seen as an asset. Identifying new profitable markets and channels to enter them, increase customer loyalty, profitability, lifetime value, and decrease risk. So the approaches that were developed in response to those things were data mining and AI. There is something known as market basket analysis that is quite widely used. I don't know whether you are familiar with it. What it means is you take any store, like Walmart. There are, I don't know how many thousands of Walmarts in USA, and every Walmart gets customers and they check out. So they may check out 2 items, 5 items, 20 items, and that is what is called a basket. So every point of sales is captured and stored. The question is, how can you make use of this information to do business better? And association rules were developed in the late 90s to do exactly that. And almost today, every vendor uses this market basket analysis for that. And the amount of data generated is very large. So think of every customer, every purchase over a year generates gigabytes of data. if you want to do multi-year analysis. So they are using this today to determine which items are sold more in which particular store based on the demographics and other information. What items are bought together, for example, so that they can store them in the same place. So there are a lot of ways in which this is being done. Text mining, graph mining is another example. Graph mining has become more popular today because of the social networks. People want to mine information from Facebook, LinkedIn, and Twitter data, for example. Recommendation systems, you may be familiar. Every time you go to Amazon, it shows you, what you could purchase, what somebody like you have purchased. This is what we call recommendation systems. And the difficulty of this is that you have to do it in real time. Amazon cannot show it to you after you leave the site. So it has to be shown either as soon as you enter the site or it doesn't make sense. Data warehousing, again, was a solution or answer to business requirements. And this was different from data mining. In other words, here we consolidated data from multiple DBMSs, Displayed Business Information Interface, exploration. Then there was complex word processing, push versus pull paradigm, stream data, accessibility using web. Ranking is very important because the reason why Google performs so much better than Bing and other alternatives that you see is because of its a good ranking capability, which is rightly. So they can somehow rank, you can try this as an exercise, give the same words to both Bing and Google and see the difference in the output you get. Most of the times, Google will give you close to what you are expecting, whereas others may or may not. Okay. So, okay, hold on. So we will try to look at very briefly, I'm going to skip a few slides, what data mining is all about. Some of you may be familiar. And I just want to point out that all of these are different from one another. This is different from search, different from querying, as well as big data analysis. We'll see that later. So hopefully this tutorial will clarify some of the fundamental concepts of the things you do, which may or may not be clear. So data mining is predicated on knowing something that nobody else knows. The key in business is to know something that others do not know. So this is a traditional example. I'll just summarize it without reading it. So you might have seen that, especially with the mobile phones, mobile phone providers, they the closer you get to your contract, for example, they try to offer you some incentive to retain you as customer. It is not that they offer this to everyone, every customer. That's not very beneficial for them. So they have to selectively determine who may be switching and who may not be switching. And if they sense that this person is likely to switch after the contract, they want to retain that customer using some incentive, then the question comes out as, how do you determine who is likely to switch and who is not likely to switch? So that is the basic sort of thing in mining, finding problems, who should be given an incentive and who should not be. How can we group usage patterns into some number of groups? Should we approve this purchase by this credit card by this user? This was even before the mining became very popular, we had something called expert systems. And American Express was one of the very first companies that used the expert system for card purchase approval. And this had to be done in real time within a few seconds. And so they were the ones who came up with an expert system to approve a particular purchase, each purchase, whether it's all the others were doing that by putting a limit on how much you can buy so that there is a cap on their liability. Why? Massive amounts of data, more and more online data. Challenge is real time versus what we call post-mortem or forensic analysis. So some things can be done as a forensic analysis just to understand things, but some things have to be done in real time. Otherwise, the value is not there. No easy way to describe what to look for. So this is the most critical thing. You cannot express this as a query, not even as a search. So you need to do this analysis without a lot of input. And that's why a bunch of different techniques were developed, like decision analysis, clustering, and other things were developed for doing different things using the same data and then figuring out how to use that. So traditional interactive approaches were not very useful because of the size and other things. So data mining is part of the knowledge discovery process carried out to extract valid patterns and relationships in very large data sets. Usually don't know what you're looking for, regarded as knowledge discovery or learning from basic facts or raw data. It is rooted in AI and uses a lot of statistics, uses techniques from machine learning, pattern recognition, statistics, database visualization. So this is the example I was telling you. How do you want to determine future behavior? And you cannot do a palm reading, human intuition, or data mining. So this was done before data mining by humans, looking at some data points, small set of data points, and figuring out what is happening. Today, the same thing is done as data mining or knowledge discovery by using more data, real data, so that the results will be more accurate. So mining has been around for quite a while. So there were a bunch of enablers without which mining would not have been possible. One is the reduced cost of storage. So you can go to larger storage systems, reduced cost of processing. So we have more powerful computers that are cheaper, ability to store, process, and manage large volumes of data and access. New techniques such as association rules I mentioned, sequence data processing, use of ontology, stream data processing, information fusion. Again, as we saw earlier, the challenges are scalability, visualization, variety, filtering very large outputs, and those things were the challenges on them. So around 1985, we had a bunch of changes that facilitated or enabled the use of data mining in a very large scale. Until then, we were doing expert system by examples. And also we are using samples. So random sampling was very important and useful because you could use smaller amount of data and hopefully get the same general inference that you would get from larger data. But once the technology improved to store more information, network them, and access them, increased processing capacity, then you were no longer limited to sampling, but you could use the entire data. So companies loved it because they had lots of data and they wanted to use all data so that the results will be more accurate or prediction will be better. So ability to acquire, store very large amounts of data plus architecture and algorithms give us the data mining. Advancements are a byproduct of changing requirements. So typically, this is what happens in a data mining. You have a data description and you have a bunch of mining algorithms. It could be clustering, it could be classification, anomaly detection, regression, subgraph. And then you get results. And then somebody has to interpret these results. That is still a difficult problem and has to be done by the human with the right background. That's why domain expertise is so critical for uh, for mining and any of the analysis tasks that we are going to talk about. In data mining, a domain expert assists the analyst to determine the best mining approach based on objective interpretation of the results is the most difficult and important. I mean, this reminds me of a story. I was visiting India and I visited a company who were getting into data mining and they had a huge contract from a company here. And they wanted to talk to me and I go there and they explained everything and I asked them, so how do you do it now? They said, we're not sure how to do it. So we know 20 different techniques that are available. So we just run the data through all those different techniques. And then we'll try to figure out which one is good. So this, in a nutshell, explains why mining is difficult or analysis is difficult. You cannot just run it through 5 or 10 different techniques available and hope somebody can recognize which one is the correct result. But that happens a lot more than one thing. So, the mining is used for customer profiling, market basket analysis, risk analysis, text analysis, fraud detection, customer relationship marketing, scientific discovery, forecasting, etc. So what is data mining trying to do? So I think this is an important aspect that I want everyone to understand clearly, because so we might have heard of this terminology separately. So one is, what is causality? So everyone understands causality, right? It is the, something that makes something happen in real world. So there is a causation between X and Y. Y cannot happen without X. So cause and effect. Heavy rains cause flooding, but the opposite may or may not be true. Flooding can also be caused by, a breach of a levee or various other. Then we have the notion of a correlation, which is a different terminology. And sort of the way we understand is kind of it's a mutual relationship or connection between two or more things and their strength. Uh, an example is as temperature go up, ice cream sales go up. Now you can have in correlation positive and negative correlations. So given these two terminology and their understanding, I have a couple of questions for the audience. One is, do the above two mean the same thing? Is causality same as correlation? Anybody? Wow. Okay. Nobody wants to take a guess. Okay, the answer is no. They are not the same. And why is that important? It's important, especially when you are doing mining. Next question. Which of the two are we trying to identify through mining? Are we trying to identify causality or are we trying to identify correlation?
Both.
Hmm?
Both.
What do you mean by both?
We are trying to identify the causality and correlation.
Well, you're almost right, but I would make a small tweak to that a little bit later. Okay, somebody else has raised the hand. You want?
Yeah, I think we try to, in research, to find correlations to maybe explain later the causality of the research.
I think you're right. You know, that's what I want everyone to understand clearly. So good that you have some good answers. So we want to identify causality through mining or for any real life application. We are interested in causality, right? Just because you see flooding uh, doesn't mean you have heavy rain. So we want to understand this, but the problem is we don't know how to identify causality in an automated manner. We just don't know still. So what do we do? We try to identify correlation and hope that correlation means there is some causality, and that is where the domain expertise comes into picture. You cannot take every correlation and say this is because of causality. That will not be correct. I think this is very important to understand. Otherwise, we can make mistakes. But we also know that correlation does not necessarily mean causality, but many times it means because we can, through programming or in by automation, we can establish correlation between two things or two data points or two sets of data points. So we can identify this, but we want this. So this is the dilemma and the difficulty for mining. So here is this is the best thing we can do. Why? Okay, here is something that I show this. I just show a couple. This is very interesting and hopefully drive home the idea. Let me see whether it comes up. Okay, so here is a website that talks about spurious correlations. And I want you to look at this. US spending on science, space, and technology correlates with suicides by hanging, strangulation, and suffocation. So this is what correlation gives you, and you should not interpret this as causality. For this, it's obvious, but for others, it may not be obvious. Same thing here, number of people who drowned by falling into a pool correlates with films Nicolas Cage appeared in. Okay, that's it. So you get the picture. I think this is one of the most important thing I will try to tell my students. When you are doing mining, be aware of it. Because it's very easy to interpret things wrongly and not understand it. And that is why it is so important to, for businesses, it means sending millions of mails or calling millions of people and not getting the expected result, doing a campaign. So I have a bunch of slides that I'm going to skip because these are mostly for an explanation that you can use. And I'm going to go to, so go to the important ones. So what is not data mining? So it's also important to understand and not get confused between some things we do, are they data mining or not? So here are a list of things. Data, what you do in data warehousing is not data mining because you're asking specific queries and doing complex analysis. So complex analysis does not mean you are inferring new data. Ad hoc querying, which is typically done, or report generation, OLAP, which is associated with data warehousing, data visualization. It's not necessarily, so you may infer from the visualization. By looking at the visualization, you may infer something, but data visualization is just a regular tool. Agents, mediators, pervasive computers. I just pushed a bunch of stuff because this is important to understand that mining is different from other types of activities that we routinely do a lot. So here is maybe after that slide. So what data mining is not likely to do. So this is kind of a very tough thing to think about, right? So this is purely my perspective. And other things that are still not possible, and if so, what kind of things are those? Certainly, mining cannot do every kind of inference. So here is sort of my take. I don't think it can substitute for human intuition and generalization. This is important to understand because when humans come up with a hypothesis, a theory, it is not necessarily based upon very large amount of data. That is the key. Whereas when machines do the same thing, they're using very large amounts of data. So humans don't work well with very large amounts of data, but they can infer things from very small samples, small examples. That's one huge distinction. But I added this line, have to wait and see where ChatGPT takes us. So ChatGPT, for those who don't know, is an AI system that has been released for some time now, which can do a lot of things that were not being done earlier. We are worried in computer science that it can do homeworks, it can write essays, it can answer any question you want. And we are worried about how to deal with that in the instruction. So this is a real thing that's going on. You should look it up. So here are the things I think a data mining system will discover. Does anyone have an example? No? So here's the first one. E equal to MC squared. Now, this is one of the famous equations that Einstein came up with. And he did not use a lot of data to come up with this equation, which is true. And the story is what happened is, to verify this particular equation, scientists had to wait 2 years for a solar eclipse to happen. And only after so he published his paper based upon his theory and intuition, but could not be verified till 2 years later. And then scientists went and did the measurements during the solar eclipse, and they verified the theory 100%. So I was in a workshop with physicists a few years ago, and I asked them this question: do you think this can be done using automation? And their answer was they didn't think so. Similarly, We have a lot of things. This is an equation from chemistry. Uh, Gravity, Newton's laws of motion. We don't know if ChatGPT is up to the task, but it's very unlikely that some of these things can be automated. Human intuition can be substituted, but it may be possible to discover things like black holes, which are heavily data dependent, and we can collect lots of data. Another good example I can think of is the value of pi. Value of pi is data driven, we know that, but most likely it was discovered not using data, but by intuition, by looking at a few samples, not looking at lots and lots of data. So we have been discussing data mining. Can you still see my shared slides?
I can still see your slides.
Okay, thanks. So, I mean, when you think of data mining, you can think of predictive and descriptive methods. And predictive methods, as the name indicates, use some variables to predict known or future variables of the other variables. Descriptive methods find patterns that may be of interest that can represent knowledge. So here are just kind of a list of two kinds of data analysis that we do. One is known as supervised. The other one is unsupervised. I think it's important to understand the distinction between these two so that you know what. So this is driven by some known information about the data, and it's called label data. So we associate what is known as a ground truth. Ground truth is something that we know to be true for this data. Some of the examples for labeled or supervised is, take for example, the weather prediction. You know the ground truth for weather prediction once it happens. So you have accumulated hundreds of years of weather information, knowing all the parameters and what was the actual weather. So the question is, can we use that information to predict future weather based upon the attributes or parameters associated with that? This is also true for loan sanctioning. For example, when you apply for a loan, how does the bank determine whether to approve a loan or not? Because they're sitting of tons of information where they know who paid off the loan and who did not. And they have more information about the individuals in terms of demographics, in terms of age and profession and others that can be used to determine. So there are a lot of examples where we have ground truth. And if you have ground truth, then the question is, how do you make use of this ground truth to generate a model that can do the prediction? So that is the supervised learning. Unsupervised essentially says that I don't know, I don't have ground truth, but I still want to get some meaningful information or inference from this one, driven by no known information about the data. It's more of an exploration, relevance, and finding new patterns relies on the multiplier. So a good example we use is clustering, for example. You don't know how many clusters are there in a given set of points. So you have to experiment with different ones and see which one makes sense. So association rules is another example of unsupervised learning where we don't know what patterns exist. Subgraph mining, graph mining is another form of it. So you'll understand more of this later in this workshop, but you need to understand the difference between these two clearly. Sample DMF approach, so there is classification. You need to understand if something I say supervised by, you need to answer. So classification is essentially classifying unknown data into a set of values that have been determined using a model. Clustering is unsupervised, as I mentioned. Association rules is unsupervised. Text classification can be supervised because you can use some data that can be even manually annotated, for example, to do that. Anomaly detection, graph mining, neural networks are usually supervised because you have labeled data using which you generate your neural network, whether it is layered or not, with various kinds of things. So deep learning, mostly unsupervised. Big data analytics can be both of these. So kind of you need to sort of know where to use which technique and why. So most of the times you'll be doing both, depending upon the data and depending upon what you want to get out of that data. So data mining is a process. Many times we only look at the algorithms that are used for mining, but it is not just an algorithm. Algorithm is one part of it. I think what is important to understand is that you have to first select the data. So I think you'll see more of that later. So it may be in a database, it may be in a data warehouse, it may be a file, it may be somewhere. You have to select which data to use. You have to do some pre-processing. Then you may have to transform data to a particular format that is accepted by the mining algorithm, and then do the mining, and then you analyze. And once you analyze, you have to see whether that analysis matches with the domain information. If not, you may have to go through this iterative process to do that. So this is important to understand. It is not just a one-shot thing, just taking whatever the output comes and then saying, I'm done. So if you want to understand the difference between mining and big data, here is one way to do that. In this example, don't worry about what is inside this one. What is important is the process, life cycle process. So here we have a data set, we have a bunch of ways to mine it, to get results, which again you have to choose which one to apply. And here, this is a much broader process or application. You may have a set of data description, and then you may have a bunch of analysis objectives, and you may want to convert this data into a model. It can be any of the models here we are shown because we are working on this one. And then you have to generate various analysis expressions, which may be one of the mining things. Then you apply them and get the results. You want to do some drill down, for example, and then you want to visualize. So this is a life cycle of what we want to do for a data, to understand it, analyze it, infer things, and do that. So this is a much larger process compared to mining. Again, around 2000, there was a lot of uh, extensions or new things that happen, like sensors and gizmos that generated a lot of data. And how the question was, how do you process the kind of data that is generated? You're also seeing a similar thing with Twitter, for example. The amount of data generated is very large in short span of time. So we had a project called Smart Home Project, Smart Home, where we had sensors in different parts of the home that were generating data. And so based upon that, we are trying to infer or predict the activities of the people who are living in the house, for example. And that is not an easy task. So this is useful for various types of monitoring. Today, this is used for example, monitoring the quality of water. Again, you get samples every minute or every 5 minutes, monitoring environmental quality, for example, monitoring bridges. They're even used for monitoring buildings, different type of things in buildings. so that they are continuously evaluated, or data is collected continuously, and inferences are drawn to see what is what is happening in the system. So this was a novel application at 2000, and mainly because of the inexpensive sensors. You might have heard of RFID tags. That's one of the sensors. So RFID tags was very popular, and today some of the garments include RFID tags to trace the lineage or provenance of where this item originated and where all it went through, and where it ends. So it is used for in pharmaceuticals, for example, to tracking drugs that may be coming from sources that are not legit. So this can also be useful in assisted living, healthcare, environment monitoring, security monitoring. So this is mainly because this data is generated 24/7, 365 days a year. So the data is coming in at some rate, and somebody has to process it. You cannot just collect it and keep it. Data semantics is slightly different from earlier traditional data, can generate disparate data, location, value, image, audio, whatever it is. So let's see data. So it's messed up on the data. So data warehousing, you encounter this because a lot of data today is stored in what is known as cloud data warehouses as well. So why do we want to, or why did we come up with data warehouse? DBMSs were pretty mature. Enterprises used multiple DBMSs many a time from different vendors. So this was a problem. This could happen because of mergers, or because one unit is using one database, the other unit is using another database, and they cannot talk to each other. They could be heterogeneous databases. Queries could not be posed across DBMSs. You could not pose a query between inventory and sales, for example, and that is very important. Analysis and report generation using multiple data were also a problem. So data warehouses were proposed as a solution to this. So briefly, this is the kind of architecture that is typically used. What you need to understand is that there are multiple data sources. Most of them are DBMSs, but it could be of different kinds of DBMSs. And there is a warehouse integrator, and there is some metadata associated with that for this to operate correctly. So you can think of this as a middleware, if you will. And then there is the actual data warehouse. So what happens is data is collected, only needed data for analysis is connected from each database periodically, because this has to be done in real time, actually, because these databases are changing every minute. But typically this is done once in a few hours so that it's easy to do that. And then this data warehouse is created, it has its own schema, and then there's a query manager and there's an analyzer. And you can also run data mining algorithms on this warehouse data. So this architecture became very popular. This is supported by almost every vendor today, every commercial vendor, and it's being used. So this is no longer a research project. It is available for usage. So a complete decision support essentially includes a data warehousing component, includes various types of information sources, and then this OLAP is the online analytical processing. This is multi-dimensional online analytical processing, and then you can generate much better, more complex data analysis from these data in these sources into this one. So this has become very popular and it's very widely used. So kind of this moved one away from individual DBMSs to collection, which is why it's called a data warehouse. Today, even though there were developed a separate system. Today, all major vendors of DBMS support data warehouses. Data marks are smaller forms used for specific purpose. Today, there is a terminology data lakes is popular, unrelated to data warehouse or storage repositories that mainly store raw data of an organization. We will come a little more of this on, on cloud data warehousing later in this workshop. So, um, so there was another technology that was found to be extremely useful. Remember, I mentioned pull versus push earlier, and this was the thing that, again, this technology has become mainstream. It is available in all DBMSs today as triggers. If some of you have used triggers in a DBMS, that's basically this one. So what is this technology? So this is the alternative to what we call the full paradigm that we saw earlier. We've been using full paradigm for a long time. We still use it. For example, when you do anything on the web, essentially you're using search or querying, which is a filter. So the question was, is there a better alternative? If so, what is it? And how do we quantify it? How do we generalize it? Where is this paradigm useful? So we did a lot of research in this one some time ago, and it was done in the context of a DBMS, even though it is today used. So all the notifications that you get today on your phone and other places is based upon this particular technology, which is the push technology instead of the pull technology. So in a traditional DBMS, you had to pull answers. You have to write a query. You had to get answers. If you did not write a query, you would not get anything. But that was not very useful. What one wanted was the push paradigm, where you get a notification or an answer, even though you're not writing a query. This is very useful and very powerful. We have seen it first in airlines and others do that. If there is a change in your flight schedule, you want to be notified because you don't want to be monitoring that every 5 minutes, every half an hour. You want to be notified by using push technology. So this is the basic idea. But in order to incorporate this idea, there was a lot of research that had go into by adding components into the system that will facilitate you to do that. And some of the components were you have to express what you want in some way, either as business rules or constraints or invariants or situations to monitor. And the system has to understand it, keep track of it. Whenever change happens, it has to push that information. So this was very important. Even today, doing it in a most general way for large systems is not very useful. You can do it in specific applications very easily. This can also be a distributed system that is based upon web. We worked and implemented such a system called the just-in-time push system, where you could subscribe to whatever you wanted on the internet. So, for example, you could subscribe to a page and say, tell me when this item, this topic on this page changes. So you may be a sports fan, you may be interested in news, you may be interested in something else. So you could subscribe to those things and you will be notified automatically when those things change without having to worry about it. So this you will see in so many different places today in so many different ways. This has also been integrated into DBMSs as triggers. So it required an event specification language, integrating it, and developing other ways of doing it. I'll not go into the details, but today complex event processing is mainstream. It is supported by many systems. The next topic is the stream data processing. The slide I showed you should have been here. So the question is, what is a stream data? Unlike traditional data that you use in MyMap, for example, you go and register for a course. You go and change a course, you drop a course, you add a course. A stream data is different from that in the sense that that is coming in as a stream. This could be from a sensor, this could be from a device such as in a Twitter. It can be from any of those things. And the question is, your stock price change, for example, can be seen as a stream. Your traffic packets, when you make a phone call, how they get routed can be seen as stream routing. So it is considered continuous as monitoring is done over long periods of time. So this posed a bunch of additional challenges that were not addressed in previous systems. For example, earlier with the DBMS architecture, you had to store everything in a DBMS and then you could query that. Now, this paradigm was no longer appropriate for stream data because real-time requirements were paramount. And when you try to put the data into a database and try to retrieve, you lose valuable time and it cannot be real time anymore. Instead, a different architecture was developed where you process the stream data directly and in real time, only using main memory. So DSMS architecture and various applications, we did some work on this one. So not addressed by traditional DBMS, new algorithms, single pass algorithms, processing without losing increment data, latency requirements were done. Here is a good example of why it is important. If you are doing a battlefield application, actually today this is true. A lot of soldiers carry multiple sensors on their body in the battlefield and the information is coming in. So you want to know whether a soldier needs help, whether he is in good shape. So soldier ID, location, heartbeat, all this is sent from the sensor to a nearby processing center and that has to be processed for various things. So this is actually happening. So imagine if you have 10,000 soldiers, each carrying 5 to 10 sensors and each sending it every 30 seconds or 1 minute, how much of data is coming in, how fast you have to process this to identify things in there. The same thing was used for Home project. Again, sensors were used for climate control, for smart sprinklers, robot lawnmowers, door lock control systems, etc. Today, a lot of these are available. You can buy some of these things and deploy them in your house and other places, so they have become more or less mainstream. So this was a research area around late 90s and 2000s. So here are some of the applications in the battlefield domain. Find all soldiers who need help, find all soldiers who need help, and all possible helpers who are within 100 meters. So you could communicate and seek help. So these are the kind of queries or situations that you want to monitor from the data that is coming in continuously and notify the appropriate person to take the appropriate steps. So this was also used for road safety. I'll skip that. Again, there were some changes. So every several years, you'll see a lot of changes in networking, hardware, software, and everything. So around 2002, network was getting mature. Before that, network was there, but it was not as stable, as reliable, and as fast. And without that, a lot of things could not be done. So this also led to the explosion of the internet. For example, internet is not possible without a reliable underlying network architecture. This project was funded by DARPA, Defense Advanced Research Project Agency, and was developed for military requirements, but then it became a dual use technology. Internet was mature, ability to access data from anywhere was possible. This is very critical. Today, you may be taking it for granted. You can access any data from anywhere, but this was not the case earlier. High performance computing required clusters. That was also very expensive, difficult to maintain, and they worked in batch mode to not access resources on demand. If you needed more resources to process, you could not do that because you could not provide that on a short notice. Cost of maintaining clusters was high. So what was lacking was an ability to use resources as needed, when needed, and pay only for the resources used. So this sort of, as you can see that, from earlier times, this was a big expectation or a tall order. So cloud computing was born mainly to meet these expectations. And today, cloud computing is there. You might be using it as, AWS or Google Cloud or any one of those things. So let's understand what cloud computing is a little bit, because you may be using it even for your usage. So here is a good example to understand why those requirements came out. So consider Wimbledon. This gets played 2 weeks in a year, 3 weeks in a year. This site gets extremely high traffic in 2 or 3 weeks. When the championship happens for these 2 weeks, this site will have high server usage. For the rest of the year, the site will have low traffic and hence most of the resources will idle. So this is the problem. The problem is the spare capacity. So you have to provide capacity for the maximum usage, but the maximum usage is not constant. So this meant that you had to buy resources even when you're not using it. So this was the case in the previous IT centers used by different companies. They had to maintain an IT center throughout the year and upgrade it and staff it, whether they used it or not. So the notion of internet scale elasticity was born, which is the ability to increase capacity without prior indication. So you just ask for the capacity and you'll get it. You don't need to tell anybody in advance that you are going to need this capacity 2 weeks earlier or 2 days earlier. So the traditional approach up to that point was keep enough spare capacity to deal with the needs of the maximum usage in a year. And this was expensive. Hardware, as you know, in our domain gets old and obsolete very fast. Maintain and managing that is difficult. Software acquisition and maintenance is also an issue. So it was not possible to outsource this just for 2 weeks. You could not say, can I outsource this for 2 weeks and not worry about it? It's not possible to rent just for 2 weeks. So these situations and needs were a side effect of internet availability and ubiquitous usage. Making things available on the web is critical. Enterprises were maintaining expensive IT shops and all the costs and headaches that came with that. Cloud computing was promoted as the answer. So cloud computing makes computer infrastructure and services available on demand, on need, and on demand. So these are the two key requirements. So you should be able to get the resource whenever you want. And also we'll see without having to indicate earlier. The computing infrastructure could include anything. It could be use of storage. It may be a development platform. It may be a database. It may be computing power or complete software applications. To access these from the cloud, organizations do not need to make any large scale capital. Kind of this was seen as a way to level the playing field for small companies. Earlier, entry into a domain by small companies was extremely difficult because of the capital cost involved in setting up the whole thing. And this came to the rest. So what is cloud computing? So you can do pay per use. But if organization need to pay only as much for the computing infrastructure as they use, it is not that we are seeing it for the first time. We have been doing it for electricity, water, and gas all along. We don't tell anybody when we are going to turn on our air conditioning. We're not going to tell anybody when we want more water. We just use it. So this is the model that people wanted for computing resources. And cloud computing was the one still that's what provides this. So to do cloud computing or to use cloud computing, a bunch of components are necessary. One is what we call a thin client. We have this thin and thick client. Thin client is one that does not have much capability, that can just communicate with something on the back end and then give you the results. But most of the times, what we use today, like a laptop or a desktop or even a phone, is not a thin client. That has a lot of capability that was not there in thin clients earlier. Grid computing or server farms links disparate computers to form one large infrastructure, harnessing unused resources. The notion of utility computing, paying for what you use on shared resources, like you pay for your public utility. On-demand resource provisioning, not static provisioning, no need to indicate. So this is what we are seeing today, and that seems to be, I only think why this has not yet happened for internet, maybe due to various political and other things, but internet could be done in the same way. You just have internet by default and then pay according to the usage. So for those who understand it, so there are, economists or accounting people call something as fixed costs, capex, and variable costs, opex. So you can see that in the traditional IT, you have a lot of fixed costs. This whole square or rectangle represents fixed costs. Variable costs change depending upon the users. But this is always fixed. This doesn't change. And the question is, this was the barrier that was there for entry, because without this, you could not do this. So essentially, what cloud computing did was to only use the variable costs and not worry about the fixed costs, because fixed costs are maintained by the cloud service provider. And what you pay is for the usage, which is the variable cost. Then you can determine how much usage you want, how much you can afford. So this is a big paradigm shift in how computer resources were being used. Uh, Another way to think about, clouds is, you have clusters, supercomputers, which are not there anymore, grids, clouds, and Web 2.0 came along. Now we are in Web 3.0. Some of these were application oriented, whereas what you see today in clouds is service oriented. So there's a difference between application oriented and service oriented. Service is provided. You can buy the service. Application, you may have to develop your own applications and manage and maintain and use them. So that is sort of the intro to cloud computing. So two things you need to understand is pay as you use and on-demand provisioning. These are the two characteristics that the end users think of, but managing and maintaining and supporting, that's a different ballgame. So what is big data? So an easy way to think is, the size is big, but it's not just the size. In addition to the size, you have diversity of data. And what you're interested in is holistic analysis. So this makes a huge difference. We know how to process individual types. We know how to process an image. We know how to process a graph. We know how to process transactions, but we still are not good at processing all of them together or even mine together to get a result. So a good example I give for this is the healthcare. If you want to do any kind of analysis in healthcare, you need to be able to bring together different types of data. It may be pathology data, it may be X-ray, it may be MRI, it may be surgery related information. So you have different types of information that needs to be looked at as a whole, not individually. And then you can make a informed decision. And that is still is quite elusive today, even with all the electronic patient records and other things. There is a big push towards health information exchange, which has happened to some extent. You can see that, but we are not there yet. So usually, big data is characterized by what we call 4 V's, and they stand for volume, velocity, variety, and veracity. So we understand volume. Volume is the size. Velocity is what we try to relate as stream data. This is the speed at which data comes. In a traditional database, the speed was slow. Students register for courses only every semester. Employee information doesn't change very much, but with stream and sensor data and Facebook data, this velocity is very high. So you need to be able to deal with that. Variety, as I was saying, you have audio, video, images that you need to deal with. Veracity is another aspect, which is the amount of trust or confidence you have in the information. So this is also very important, because if you take data that is not trustworthy, your analysis results are also not trustworthy. And you need to be able to differentiate. This is one place where the provenance, as we call it, or the lineage, can play a significant role in understanding where the data came from, whether the source is trusted, how much they can be trusted, and how much importance can you place on the analysis you are doing. So this is important to understand what differentiates what we today call big data from other kinds of data. So we are good at processing these things individually. What we are not good at is processing them together. So in the literature, if you see, there are so many other V's that people have tried to add to this. At least any word starting with a V, they have tried to add variability. But I think they do not characterize big data. So where do big data come from? So we earlier gave this, Hadron Collider, uh, telescopes, various telescopes that we send out generate tons of data. We have 12 plus terabytes of tweet data every day, 25 plus terabytes of data every day from other sources, billions of camera images, satellite images, probably. So the amount of information generated is not the problem. And this will keep getting larger and larger. The problem is, how do we use this information rather than just dumping it and forgetting about it? Just as an anecdote, NASA, which collects, so they don't store the data on disks. Why? Because the size of the data cannot be held on disk. So they have warehouses, not data warehouses, physical warehouses with thousands of tapes on which the data that they have collected is stored. So researchers can go and request that information and get that information. So the amount of information is so large that they cannot just keep it online for everyone to use. So these are just numbers in terms of this one. So the big picture, sort of my view of the big picture, which is very similar to What I showed you earlier is the following. So it's the same problem, but the input has changed. The input is no longer a single type of data. It can be structured data, it can be image data, it can be audio, video data, it can be unstructured data. And you have you're just sort of blindly exploring data, but you have some analysis expectations, what you are looking for, what you want to look for, plus do other kinds of analysis. And the ultimate goal is to extract and visualize knowledge in a meaningful way. So we call it transforming disparate data into actionable knowledge. So actionable is important. If you cannot take action based upon the knowledge, then it's not very useful. So it can be any kinds of data. So this is the sort of the big picture for what all of us do, whether you're in earth science or so on. So it may be a small subset of this, but this is the bigger picture. So you need science, you need abstractions, you need various theories, you need analytics, different algorithms, different types of algorithms, faster algorithms. So you need both of them in order to get this one. So what is data science? So data science or analysis is not new. Again, it's the same things, but emphasis is on understanding and managing data, slicing and dicing data, compare human and machine engineering, data mining, both an exploratory and discovery component. Now we are combining all aspects of application business with computer science and statistics for inferring or discovering and building. So this is the sort of the holy grail for data analysis. So enablers, again, looking at what kind of technologies have brought us here. Similar to what we saw, but you'll see that the technologies are slightly different. So this is one way to think of. It's a combination of synergy between computer science, mathematics, and business application. And in terms of various specific techniques, machine learning techniques, software development, human in the loop. This is very important because still data analysis, I think, cannot be done without a human in the loop. I mean, we want to minimize the role of the human, but we still don't know how to eliminate it because somebody has to interpret and understand and think whether it is right or wrong. So to me, data science and data is not a single approach or a single solution. There is no silver bullet. It's a complex process involving many moving parts, using extending not only current approaches but also developing new ones. Because we still do not have all the technology to combine different types of data, and they still need to be developed. If you will, it's a suite of approaches for modeling and analyzing. So modeling is very important. You cannot just use data without modeling it in some way that helps you process it or analyze it better, a diverse complex data set for a given set of analysis. So that's what it is. What each of us may be doing may be a small component or sliver of that. So given the one way to describe it is given a complex data set plus analysis objectives, determine or develop modeling abstractions, analysis methods, and visualization. So kind of this is kind of the task for computer science people, but the consumers of all of this will be people who use it in biology, earth science, water management, plus you may be developing your own techniques that we do not understand or we don't know how to develop. So again, going to the same diagram. So this is big data analysis versus mining. So to sort of summarize what I have covered in the last hour or so, so we have sort of covered what sort of things happened between 1970 and today. So we started with file systems before this. So before 1970, everything was done using file systems and writing applications and other things. And then came DBMSs, hierarchical and network before that, and relational. So they made life easier by supporting a bunch of. So what you see on top are abstractions that are supported for end users. What you see at the bottom are abstractions that are supported underneath or automated as part of the software, middleware, whatever you want to call it, in various ways. So the abstractions that were supported for relational was multiple users. We'll come back to this a little bit later, durability and things. Then came data warehouses, vertical integration of multiple data sources into a useful database, multidimensional analysis. And one of the challenges was how to keep the data fresh. If you are collecting data from multiple sources, you have to make sure that data is not old. And it's still a problem today if you think about what Google does, right? I believe it takes Google about 6 months to scan the internet for changes. 6 months is a long time. So that's why when you get a result from Google, it may be a little bit older. It may not be fresh. But for the kind of things you are doing, it doesn't matter. But if you are making some important decisions and other things, freshness is very important. So Google also and all other, they use web crawlers. They have very sophisticated algorithms to determine which site should be crawled more often, because that site changes more often than from other sites. It's not that they just go in a round robin fashion. That is not the case. So keeping data fresh, and this is also an issue with ChatGPT. I don't know you are aware of it. So it seems people were asking questions, and ChatGPT uses data that is 2 years old, because that has not been integrated into its vocabulary in some way. So when asked about something, the information it was giving was certainly more than 2 years old. So that's an issue with data mining. Became very popular and widespread and used on a very large scale. In the 90s, it was there even before, even in the 1960s, there were mining algorithms that were being developed, unsupervised, market basket, various things. Then came stream data processing, real-time data processing, various latency issues, quality of service specifications. Then we are a big data analytics. I only listed a few things that we do in the IT lab, but there are more things than this one for this one. So the other thing I should maintain is, so that the whole point, I feel that without understanding the past to some extent, if not in detail, it's very difficult to appreciate the present and plan for the future. So what I have tried to do, I think, as part of this exercise is to give you a kind of a roadmap of how things happened in a short way, and why we are here, what contributed to where we are today. The other thing also I think is very important is I try to emphasize this to my students is technology provides solutions. but it does not necessarily solve problems. I think there is a big difference between solving a problem and a technical solution. I think it's important for us to understand the difference. A very good example is code. We have solution, but it certainly has not reached everyone, not because there is no solution, but various things, cultural, political, financial, things come in the way of solving problems. This is true for every technology. Developing the technology is one problem. Using that to solve problems, real problems, is a unique challenge in itself. And I think we as technology developers and users should understand it clearly. Just because you come up with something doesn't mean the real problem goes away. Okay, so now in the rest of the time, what I want to do is to focus a little bit more on the details of the analysis, which we mentioned earlier. So descriptive analysis is a method for quantitatively describing the main features of data. Typically use statistics and statistical measures for doing this. So for example, you can apply descriptive analysis to census data that you're familiar with. Can compute averages, frequency distributions, percentage, histograms, distributions of household income, various type in there. So you can play with the data and determine or a bunch of useful information. Prescriptive, on the other hand, is more of prediction of what action you need to take based upon that, finding the best course of action for a given situation. It may be preceded by descriptive analysis. It's a process-intensive task, analyzes potential decisions and interactions between decisions. You may have to do it in real time. Goal is to prescribe an optimal course of action. This is what we call actionable decision. You may use optimization, simulation, game theory, and of them you should not. You should be comfortable with them. You don't know what kind of analysis you'll be doing and when you will be doing. So here is an example. You have the latest census data. Suppose say you want to know the top 5 states with largest increase in population. Now, this can be done with descriptive analysis, right? You can compute the changes that have taken place. You want to know which states how income is likely to rise in the next 10 years. So this question is different from the previous question, but there is a qualitative difference between the two. This can be done with descriptive analysis. This cannot be done only with descriptive analysis because you are predicting what is happening in the next 10 years. You want to explore the rate of something. In general, you can use both of these. Both exploration or search space can be large. So need to have some idea of what you're looking for and then do that. So I hope I'm able to convince or convey the difference between these two types of analysis. The other thing that you should also understand is data analysis can be done in many ways. You can do it manually. It was being done manually. And the advantage of doing manually is that the person who is doing it has understanding of the problem and the context, can use intuition, match real world semantics, can explain your analysis, reasoning, but it can be error-prone. Remember the NASA Mars orbiter mission, where British measures were used instead of the US metric system, and the orbiter exploded. Cannot deal with large amounts of data. Humans are not good at dealing with large amounts of data, but they can understand small amounts of data in a different way. Complex computations are also difficult. So manual involvement is still needed in some way. You cannot completely through it. If we look at automated approach, that's what a lot of us do today, avoids computation errors, assuming programming is correct. This is a different issue. Can deal with very large amounts of data, analyzed in multiple ways, takes less time, but someone has to come up with algorithms. Someone has to design the program of the system. Someone has to validate the system. Someone has to sanity check before using the stuff. So these are still difficult to do in an automated manner. Human in the loop or hybrid mode, this is very much the essence of data science. Humans play a small, but I think they play a critical role in the analysis that is done. So there are advantages to all of these different approaches. So let me illustrate it with a known example. Suppose say I'm doing a manual approach or analysis. Suppose say I'm teaching a course and I'm grading it. So you're all familiar with that. So I can say it can be done with absolute methods. Some number, you'll get A, B, and certain numbers in B, C, D. But humans can deal with small variations. What if somebody gets 84.9? Should that person get a B or an A? So this is where humans can adjust or do things slightly different from this one. Another example, suppose say I'm using a curve, which I typically do, saying class average plus one standard deviation is A. Again, what if someone missed A by a very small amount? Can look for separations, can make exceptions based on interaction, effort put in, class participation, types of questions asked. So manual approach has some merits, but you cannot scale it. What if the class average is 82%? I had one very great semester where the class average was extremely high, unexpected, close to 90%. And the standard deviation is 8. So, everyone has done so well that you don't want to just apply this rule and just say that's it. Should one give 8 to 90? So this is the kind of the problems or issues that you need to understand when you're doing manual. Advantages of automated approach are fast, can generate reports for human consumption, can visualize. We use spreadsheets and graphs a lot, easily compare alternative analysis, but sometimes the difficulty is in the explanation. This is very true. One of the reasons neural networks are very popular, deep learning is very popular, but still we have a lot of difficulty understanding why it works. It works for certain trained labeled data set, but if the data set changes, you have to come up with a new neural net. Generalization is difficult. Should not blindly assume the output is correct. Need sanity check. Validation on small sample data. Need to be aware of changes in context, expectations, etc. So data analysis in the net is not as easy as you think. Running a program is easy, looking at the results is easy, but when it comes to actual understanding, interpreting, and analysis, a lot more has to go into it before you do that. So the bottom line is we want to process large amounts of data. We want the flexibility to slice and dice data in many ways. We want to do it fast. We want to do it incrementally. That's very important because data is coming and you want to be able to add the latest data and look at how things have happened rather than trying to process all data, which takes a lot of time. We want an efficient approach. We measure that in terms of performance, speed up, and scalability. We also want liability if something goes wrong. So how many times you have heard somebody say, oh, this was a computer problem? And there's nothing like a computer problem, right? It's whoever developed the software did not develop it right. We want to outcompete others in the same business. So, okay. So then the next question, I think this may be better understood after tomorrow's Python, but typically we use Python. But the choices are in a Python, RStudio, Pandas, others. Which one is better? Actually, it depends upon who you ask and what needs are. All are useful. Learning curve varies. That is the key. So learning curves, we'll discuss this later. So what I have now is in the time left two sort of examples. So this, I'm not assuming any Python background for this, just to show you, I mean, these are class projects that I have given to data science course that I was talking about. They learned Python. While learning Python, they were doing some projects to learn analysis, like the way I have described earlier. And these were used as sample projects. So one was on census data analysis. One is, so we are given, so there is data for 1990, one later one. So I gave them only 32,000 rows, but if you look at the entire census data, it's much more than that. The original data has already been pre-processed as follows. So discretized gross income into two ranges. So this is what the data was. Convert you some changes, some formats into this one to make it easier. Convert unknown to question marks. Sample input comma separated. So this is how the input looked like. So each line contained some number of attributes, as we call it. So these are comma separated, essentially CSV files, 32 private, blah, blah, blah. So the question is, if you are given only this, what do you do with that? So this is where, wait a minute. Okay. So if you are given only this, it's very difficult to understand what it means. This is where, as we shall see, metadata and creating proper metadata is extremely important for someone to understand, even for as simple a data set as this, where you can guess a few things. But in more complex data sets, it's even more critical. So here is the description. So typically, this is what you see. So these are the descriptions of each field. So for example, in the 32 is the work class and others. So there are so many types of work class: education, education number, marital status, occupation, so on. So this at least tells you some indication of what it is. And then you can use that information to understand the analysis or even what to do the analysis with. So what I asked them to do was to do two or three kinds of analysis. One was they count the number of people in the following groups. In age less than 20, 21 to 40, 41 to 60, just to find the kind of age groups and the population among these age groups from the data that is given. Draw the histogram to understand it. So that was analysis one. Analysis two was for the above age groups, find the number of people in each of the following professions. So kind of this is what we call drilling down. So you have a result and you want to understand more about the result in these groups. How many people work for this particular type of employment, this employment, what do I separate pie chart for each? So this was to give them an understanding of one, how to use the data, understand the data, and how to do these are simple analysis using packages, and also how to visualize it so that it's easier to understand. So this is for drill down. Analysis three was identify top 5 occupations for the population. So this is more of a ranking question. So we want to know which type of occupation occupies the highest spot and so on. So, so we also gave some idea of how to do that. So I won't go through the Python code. I think you will learn all about this tomorrow, and you'll be able to do this. So here is the histogram analysis. So you can clearly see from this, there are more people in the age group 21 to 40 in this data set than other age groups. So there are very few people who are less than 20, very few people greater than 61, but the bulk of the population is in this one. So again, we were using packages to plot this and see how you do the analysis and representation. So the second analysis essentially used pie charts, where you can see that for this group, what was the breakdown for different kinds of occupations. So this is self-employed, private. So private seems to be more among the younger people as compared to the older people. And you can also see that as the age changed, the more people migrated to government jobs. So you can see that kind of, stability or whatever it is, you can see some understanding of how things are happening. For the last one, we had top 5 ranking. So professional specialty job was the highest, then craft repair, then managerial executives, administration, and sales. So this is how the data happened. So another way to look at it, so we also use different visualization techniques. So this one is known as word cloud. You might be familiar with it. You'll see in TV news and other things which particular word appears more prominently in any discussion and other things. It's easy to understand, for example, the size of the script or the font size, not the font, but the size indicates that it's more prevalent in that. So here, for example, this one has the bigger size, then comes craft repair, then this one. So this is a very easy way to visualize the results of the analysis so that you can immediately see, for example, private house like protection service is very low, armed forces seems to be very low in this data set. So they did this over a couple of weeks and then made a presentation and submitted the report. So kind of what we want them to do is to go through the entire life cycle, pre-processing the data and even trying it on a small sample for sanity checking, because we want to make sure that their results are correct. Because when they write a small program, even if they use packages, we know packages are correct. That doesn't mean the rest of the program is correct. So that's an important thing we try to emphasize. So second one, this is more about prescriptive analysis. So to give them a taste of how this analysis differs from the previous one, for example. So we gave them airlines data, a little bit older, that was available. So they're given large airlines data indicating the flights operated by many airlines. Purposely, we replaced the airline names with anonymize them, if you will, because we wanted them to find out which airlines it is. The data set contains the following information. So it has comma separated field, but there is also a description of what they are. So this is the sort of the extent of metadata that we typically find in the computer science literature, which is not a whole lot compared to what you're trying to explain with say principle. So this certainly is useful, but not sufficient enough to do anything. If there is no provenance, whether there's nothing even as part of it. So the analysis that we asked them to do was analyze two specified airlines given to them, construct a graph or a graph data structure for the airline with airport code as the vertex, draw an undirected graph between 2 points in each line. Since many Python packages only accept integers as vertex, you may have to map the 3-letter code. You can use dictionary information. So we gave some tips as to generate characteristics for this airline route. This will help understand some of the characteristics of the data, interpret them from an airline's operation perspective, and see whether you can identify which airline it is based upon this information. So find the top 3 to 5 nodes from where there are more flights than others. These are termed hubs, so you can use nodes and functions for that. So again, what to use, when to use, for what for is an important aspect. So once you have the top K hubs, try to identify the airline that you are working on. You can use any data that is available on the internet. For this purpose, we will give you a file that maps airport code to airport names and cities. In the next step of the analysis, your goal is to identify or predict the next hub for airline expansion. If the airline wants to expand their operations, which city would they want to choose and why? For this, you can use demographic and other information that is available from it. So again, this one is not just understanding the data, but it is more than that, trying to figure something out that is not obviously part of the data that is there. So the approach was given. So I'm going to skip some of the things and show you the results. I'm going to skip that Python code one. Okay, so here is a graph. Now there are using those tools, you can expand or zoom and in little things. You can see some nodes that have very large number of edges. So LHR happens to be London Heathrow Airport, for example. So you can see that this is one of the prominent airports for this airline. DFW has a lot of lines. This is another prominent airport. Miami is one of them. And I can see those three clearly. So you can see from this, you can get an idea as to which airline this could be based upon the information that you're seeing. So again, if you use the word cloud, you can see more information than the graph. So you can see DFW, Miami, DC, where is hello channel? I don't see. But this is for AL1. This is for AL3. This is a little more difficult to see, but you can see it from here. You can see Atlanta as one of the big airports, JFK. DTW is Detroit. SLC is Salt Lake City. So I think so. You can see that from the data set, you can get this and then further analysis. So we also do various kinds of analysis to understand the data set, number of nodes, number of edges, diameter, density of layers, component graphs, degree graphs, average degree nodes. So all these information are useful in different ways. Maximum degree of graph node, that means it has 184 flights or connections with them. Similarly, for AL3. So I don't expect you to know this notion of degree centrality, but this is one that detects how many edges are there for a node, and it is ranked by the number of edges, which happens to semantically coincide with the hubs for an airline. So based upon that, so for example, here are the airport and the airport names, degree centrality. So based upon that, you can identify which airports are the top 3 airports. And given that, you can also identify them as airlines, American Airlines. So this is just an exercise in trying to put things together and make sure that your analysis makes sense. So similarly for the next one was Delta, for example, because Atlanta, Detroit, and Salt Lake City, they for this. We know this. We know this if you fly based upon. So the next one was the more. Oh, oops. Oh, okay. Okay. Approach for predicting the next hub. This is the important thing. The next hub for the Delta Alliance can be chosen from any of these three. Now, these were not the top 3 hubs here. These are taken from this one, but this is based upon some additional information in terms of population, education level for that particular city, average mean income, and various other things. So based upon that, you can choose which ones can be used as the picture. So kind of these are two. One more analysis I'm going to show on Thursday after Python is done. We'll appreciate it much better. So I'm going to stop here, and it's a little bit earlier than uh, I should, but I'll be happy to answer questions for the next 5, 10, 15 minutes to clarify anything that was not clear in the presentation.